Hey everyone, welcome back to the channel. In this video we're going to talk about why the heart can't be tetanized. And this is a continuation of my previous video where I talk about fast response cardiac action potentials, where I explained a little bit there about why the heart can't be tetanized, but I think it's just easier if I compare it to skeletal muscle so that we can understand it a little bit better. So on top we'll have skeletal muscle and on the bottom we'll have cardiac muscle. And remember, this is over time, which is in milliseconds. And in red, we'll talk about action potentials in millivolts. And in blue, we'll talk about muscle tension, which we'll use the denominator N as for newtons. And for newtons, there's no specific number because it really depends on the action potentials and the amount of tension for the muscle. So it's dependent on muscle tissue and action potentials. So when it comes to skeletal muscle, when an action potential fires, it's essentially this short little blip of electrical activity where the cell membrane will suddenly increase and then drop. And when this occurs, it goes from about negative 90 millivolts all the way up to about just above zero, so it essentially becomes neutral. And this is due to opening of sodium channels and other channels that increase the cell membrane potential, which is the electrical charge difference between the inside and outside of the cell. You can see here that the action potential is very short-lived. It only lasts about a couple milliseconds before it then returns back to baseline. So just after the peak of the action potential, you'll start to see the beginning of muscle tension as it ramps up, as our myosin actin complexes start to engage. And then the peak tension will occur slightly after the peak of the action potential. So there's a slight delay here. But with this tension, it's still not a very strong response here. And say we wanted to lift weights and lift a bit more with a bit more tension, then what happens is rather than have a long-lasting action potential, our brain sends signals that lead to increased firing of the action potentials to the muscles. So you can see here that as there's increased firing, there's this increasing tension that sort of moves up. And this is called summation, because each individual action potential leads to more tensioning of the muscle. So it's summative in terms of the tension that's applied to the muscle, so you can generate more strength to lift more weight. While when we had the single firing of the action potential with the single tension of the muscle, this is known as a twitch. Now if we take those action potentials and move them closer together, so there's increased firing, you can get this summation, but it happens in a rougher, closer together period of time as the muscle tensions. And this is also known as rough tetanus or unfused tetanus. Now you can move them even closer together and you'll get a more smoother tensioning of the muscle, and this is known as smooth tetanus or fused tetanus. So rough tetanus and smooth tetanus aren't necessarily disease processes, but you may see this, for example, if you're at the gym. You'll more likely see this rough tetanus, say if you're extending a muscle and then slowly releasing it. You may see quivering or tetany of the muscle while it's trying to maintain tension, but the action potentials are not close enough to create a smooth contraction. But then we go to the extremes, where if you have the action potentials that are very close together and they're sustained, then the body or the muscle can then be put into a tetanus state or a tetanic state, and this can be a disease pathology that can then lead to death over time. So the tetanus where the muscles are always contracted, essentially the action potentials are so close together that they don't have a chance to relax. But you can also get a sustained unfused tetanus as well, where the action potentials are just slightly apart that the muscle begins to relax before the next wave of contraction occurs. So the reason why skeletal muscle is prone to tetanus is because the absolute refractory period of the muscle, meaning the period of time that the muscle can't be re-stimulated, is very short, only 1 to 3 milliseconds depending on the type of muscle and where in the body the muscle is found. And it's shorter than the time it takes for the muscle to essentially contract and then relax. What this means is that because the action potential can fire very rapidly, the muscle doesn't have time to relax before the next firing, meaning that you then get sequential increasing of firing and tone of the muscle, as you can see in summation. And then if it's fast enough and rapid enough, you will then get this smooth increasing in tone and then a steady, consistent tone throughout the muscle that isn't relaxing, which is normal when it comes to trying to lift weights in our body, trying to maintain positions and postures. However, it becomes pathological when your body is unable to relax, such as when someone does suffer from tetanus. However, despite this, when it comes to the cardiac muscle, even if someone does suffer from tetanus, the heart isn't affected. And this is due to a protective mechanism of the heart in the way that it manages its action potential. So essentially, if you start at negative 85 and we go up and we depolarize to about 40 to 50 millivolts, you can see here that there's this plateau phase that occurs during the cycle. And I talk more about this in my video about fast response cardiac action potentials, which is linked just above. But essentially, there's in yellow an absolute refractory period and in green a relative refractory period. And during the absolute refractory period, which is about 200 milliseconds, the cardiac myocyte cannot be stimulated again. It's in this plateau phase where there's enough sodium channels that are currently closed where it can't depolarize. And then in the relative refractory period, which is about 50 milliseconds in green, if a strong enough action potential comes through, then it can potentially depolarize. But importantly, you can see here in blue, the tone of the cardiac muscle, it starts just as the depolarization phase happens at the peak, and then the time it takes for peak tension and then relaxation happens around in this absolute refractory period. So then if you were to draw out rapid succession of the action potentials, you can see here that there's enough time for the heart muscle to contract, relax over and over again as it normally would, despite there being rapid action potentials in sequence. And this is due to the protective mechanisms of the heart due to the plateau phase and the prolonged absolute refractory period, which is longer than contraction and relaxation of the cardiac muscle. To summarize, the key difference that protects the cardiac muscle from tetany, unlike skeletal muscle, is that cardiac muscle has a longer refractory period, while skeletal muscle has a shorter refractory period, which serves its own purpose in that it allows skeletal muscle to have different levels of tension when we need to apply different forces. But when it comes to the heart, it's not really an issue that the heart needs to worry about, but rather it serves a protective role for the heart to stop arrhythmias from developing and to keep the heart in rhythm. The heart has other mechanisms that it uses to increase its contractility depending on the fluid status of the body or the preload and afterload that it experiences, which I'll talk about in later videos. So that summarizes the video, and hopefully that makes it a lot easier to understand why skeletal muscle is prone to tetany unlike the heart. If you have any questions, anything you want to add, or anything you want me to cover, feel free to drop it in the comments. I always read my comments and I try to reply. And I'll see you guys in the next video where we'll talk more about these protective mechanisms of the heart.